Welcome back. Our first topic this week is graphs of the other trigonometric functions. We will talk about four functions: tangent, cotangent, secant, and cosecant. Let's start with the tangent function and summarize what we know about it. Let's first of all recall our definition of tangent through the unit circle. If we have the unit circle centered at the origin, recall that tangent has a very clear geometric meaning. If I draw a straight line that is vertical and passes through the point 1, 0, that line can be viewed as the tangent axis. Meaning what? Meaning that if I have an angle x, measured as we always do from the positive direction of the x-axis, then this distance here is tangent x. From here, it is also immediate that tangent equals sine x over cosine x. Why is this distance, by the way? Ratio of sine x and cosine x. Where is sine x and cosine x? Well, the coordinates of this point are sine x and cosine x, which is why in this right triangle, this distance is cosine x, and this distance is sine x. Because these two right triangles, let's give them names. OAB and OCD are similar. And writing the ratio of corresponding sides, we have, for instance, that AB divided by OB the length of AB divided by the length of OB equals the length of this side, CD, divided by the length of this side, OD. On the other hand, AB, as we said, is sine x. And OB, as we said, is cosine x. Now, CD is tangent. And OD is 1. So tangent is indeed sine over cosine. All right, let's now talk about the basic facts about the tangent function that we know and that will help us figuring out what its graph looks like. First of all, let's talk about the domain of tangent. The domain of tangent is easy to find once we again recall that tangent is sine over cosine. So the domain of tangent is simply all the real numbers except those where cosine x is 0. Where is cosine x 0? Cosine x is 0 at 2 points on the unit circle. And we talked about this many times in the past. Both points could be described as pi over 2 plus any integer multiple of half a revolution, either this direction or that direction. If I start at this point and make any integer multiple of half a revolution, I will end up either at this point again or at that point. These are the only 2 points where cosine x is 0. So I can write that domain of tangent is all the real numbers except those of the form pi over 2 plus pi times n, where n is an integer. That is the domain of the tangent function. Something else here is true, which we will use. It's interesting to see what happens when x is close to numbers of this kind. Tangent is sine over cosine, and when the argument of tangent x is close either to this point on the unit circle or to this point on the unit circle, the numerator of this fraction sine is close to either positive 1 or negative 1. And the denominator of this fraction cosine x is close to 0. Remember, cosine is the x-coordinate. So when you're close to either of these 2 points on the unit circle, the x-coordinate where you are is close to 0, either positive or negative. So when you divide a number that is close to positive or negative 1 by a number that is close to 0, positive or negative, you will get a number that is huge by absolute value. It could be positive or negative. So positive or negative infinity. I encourage you, for instance, consider the following table and work with a calculator. Consider the following table of numbers. Let's say we're taking x to be pi over 2 plus 0.1. What will be the value of tangent x? Then take pi over 2 plus 0.01. Then take pi over 2 plus 0.001. Pi over 2 plus 0.301. You will see that the values of tangent will be negative because this is in the second quadrant, pi over 2 plus something. And they will be negative but huge by absolute value. For example, tangent of pi over 2 plus 0.1 will be negative approximately 997. If you add another zero here, it will be approximately negative 100. If you add yet another 0, you will get approximately negative 1000. You add another 0, you will get approximately negative 10,000. If you add yet another 0, you'll get a value that's approximately negative 100,000. And again, it should be clear why. All these numbers are greater than pi over 2, but very close to pi over 2. So we're talking about points here on the unit circle. For any point here, sine is close to 1. Cosine is close to 0 but negative. When you're dividing a number that's close to 1 by a number that's close to 0, division by a number close to 0 always causes an explosion. The ratio where the denominator is close to 0 will always be huge by absolute value. It's also interesting to see what happens when you look at points on the other side of pi over 2. We can actually try numbers here near negative pi over 2, just out of curiosity. Slightly less than negative, so we want on the negative side. Negative pi over 2, but in the fourth quadrant. So negative pi over 2 plus something. That'll be maybe, yeah, let's look at pi over 2 on the other side. So pi over 2 minus all these numbers. Let's see what happens then. This time we will be in the first quadrant. And we expect values of tangent to be positive. And as we will see, they will be huge positive. So this is roughly 997. If you add another 0, this is roughly 100. If you add another 0, this is roughly 1000. Add another 0, this is roughly 10,000. Add another 0, this is roughly 100,000. So, as expected, when we are close to pi over 2 in the first quadrant, values of sine are close to 1. Values of cosine are getting closer and closer to 0, but stay positive. They stay on the right of 0. So the ratio of sine over cosine is essentially numbers close to 1 are divided by numbers close to 0. Of course, the ratio will be numbers that are close to positive infinity in the sense that they are positive and getting bigger and bigger. This could be written in a very formal way. I could write this formally by saying that limit of tangent x as x approaches pi over 2 from the left is positive infinity, and limit of tangent x as x approaches pi over 2 from the right is negative infinity. In general, the same type of argument shows that limit of tangent at any such point of the form pi over 2 plus an integer multiple of pi. So these are 2 points on the unit circle. Whether you are from the right or from the left approaching any of these 2 points, the value of tangent will be huge positive or huge negative. And that implies immediately, by definition, that any such line any such vertical line x equals pi over 2 plus pi n, where n is an integer, is a vertical asymptote. Already we see a very interesting function here. We never in the past had examples of functions that have infinitely many vertical asymptotes. Tangent is one such function. The other 3 functions we are looking today, cotangent, secant, and cosecant, will also have infinitely many vertical asymptotes. So this much we have established. Every vertical line pi over 2 plus pi times an integer will be a vertical asymptote, in particular taking here this integer to be 1 and negative 1, rather 0 and negative 1. We get vertical asymptotes pi over 2 and negative pi over 2. Right? When n is 0, we get pi over 2. When n is negative 1, we get pi over 2 minus pi, which is negative pi over 2. All right. We'll get back to asymptotes in a minute. After we talk about the periodicity of tangent. We already talked about periodicity of tangent in the past, but let's remind ourselves that tangent is a pi periodic function. That is again easy to establish using the unit circle. Let me copy this picture again. If you try to compute tangent of x plus pi, that is by definition sine of x plus pi over cosine of x plus pi. But how can we express sine of x plus pi and cosine of x plus pi over sine x and cosine x respectively? Well, if this is x, where is x plus pi? X plus pi will be a point diametrically opposite to x, because pi corresponds to half a revolution. And if we ask the question about the coordinates of this point, it's easy to argue that by equality of triangles OAB and OA1, B1, they are indeed equal. These angles are equal. This is one straight line. These angles are equal. Both are right triangles with equal hypotenuses. Hypotenuses are both 1. So these triangles are equal. This distance, therefore, is the same as this distance. And this distance is the same as this distance. Therefore, the coordinates of this point are negatives of the coordinates of point A. In short, the coordinates of point A1 are simply negative cosine x, negative sine x. That explains immediately that cosine of x plus pi, the x coordinate of this point, is negative the x coordinate of this point, which is cosine x. And likewise, sine of x plus pi is the y coordinate of this point, which is negative the y coordinate of this point. And the y coordinate of this point A is sine x. So sine of x plus pi is simply negative sine x. In other words, on the one hand, the coordinates of this point are negative cosine x, negative sine x. But on the other hand, they are also cosine of x plus pi, comma, sine of x plus pi. So when we apply this here, we get that sine of x plus pi is negative sine x, and cosine of x plus pi is negative cosine x. The minuses, of course, cancel out. We simply get sine x over cosine x, and that is indeed tangent x. So what we get is that tangent of x plus pi equals tangent x for any x in the domain of tangent. It's a little bit more involved to show that no positive number smaller than pi has this property. And so pi being the smallest positive number with this property is the period of tangent, but we will take that for granted. So tangent of x plus pi is tangent x, and no positive real number smaller than pi has this property. Therefore, tangent is a pi periodic function. Let's get back to our fact, to the fact we just established, that pi over 2 and negative pi over 2 are vertical asymptotes of tangent. There's no it actually confirms our previous finding, because pi over 2 and negative pi over 2 being vertical asymptotes, coupled with the fact that tangent is pi periodic, indeed implies that pi over 2 plus pi is also a vertical asymptote. That's 3 pi over 2. After that, 3 pi over 2 plus pi is 5 pi over 2 is also a vertical asymptote. In short, the distribution of vertical asymptotes follows the periodicity of tangent. Here my scale is 6 squares equals pi. So 1 square equals pi over 6. This asymptote is negative pi over 2. This asymptote is negative 3 pi over 2. And this asymptote is negative 5 pi over 2. What else do we know about tangent? We also know that tangent is an odd function. That is because tangent of negative x being sine of negative x divided by cosine negative x. And sine being an odd function and cosine being an even function, implies that sine at negative x is negative sine x, and cosine at negative x is cosine x. That is by definition of even and odd functions. That is, of course, negative tangent x, and that is for every x in the domain of tangent. And that is also clear from the unit circle, because if that's angle x, then this here will be angle negative x. And again, by equality of these two triangles, OAB and OA2B, we see that, why are they equal? They're both right triangles with these two angles equal and equal hypotenuses. That's enough to conclude that they're equal as triangles. So the coordinates of point A2 are therefore cosine x, negative sine x. So we conclude immediately that cosine of x equals cosine of negative x, because on the other hand, this is cosine of negative x comma sine of negative x. So the first conclusion is that cosine x equals cosine negative x, implying that cosine is even. And the second conclusion is that negative sine x equals sine of negative x, implying that sine is odd. And also from the picture we see that the triangle OCD happens to be equal to triangle ODC2. In particular, that distance CD is equal to the distance C2D. These triangles are again equal as having the same acute angle, being right triangles and sharing one leg. So the other legs are also equal, but one leg is tangent, the other is tangent of negative x. So these distances being equal implies that tangent x and tangent of negative x are equal by absolute value and different only by a sign. Tangent x equals negative of tangent of negative x. So if we gather all that together, we see that it's enough to draw the graph of tangent only between 0 and pi over 2. Because if we have a picture here, by the fact that tangent is odd, we can reflect this picture about the origin, get some picture here, and then we extend tangent by periodicity into each lane here. So how does tangent look like between 0 and pi over 2? Let me copy this picture again. So let's think. Tangent of 0 is 0. That is because sine of 0 is 0 and cosine of 0 is 1. What happens then in the first quadrant? As x starts growing, sine x as x grows from 0 and approaches pi over 2 from the left, sine x grows and stays positive, and cosine x approaches 0 and stays positive. Therefore, the ratio sine over cosine grows from 0 to positive infinity. right? 0 is here. As we grow in the first quadrant, the numerator gets closer and closer to 1, but the denominator gets closer and closer to 0. And as we saw, that causes a quick explosion, a quick blow up in the values of tangent. Oh, that was supposed to be, by the way, minuses. We want to be in the first quadrant. As we approach pi over 2 staying in the first quadrant, the values of tangent quickly explode to infinity. So we get sort of a function that remotely looks like cubic parabola. And that's it. We don't need to think any more than that. Because by oddness, by the fact that tangent is an odd function, I simply take that thing. By the way, there's one important point here. Tangent of 1, tangent of pi over 4, excuse me. Halfway in the first quadrant, when this angle is pi over 4, and both sine and cosine are equal to root 2 over 2, of course tangent is 1. So we can show that point. Well, assuming that this is 1 pi over 4 and this is 1, so the curve will go like this. And now we simply reflect that thing about the origin. So in particular, I want to find the point negative pi over 4, negative 1. That is one branch of tangent in between negative pi over 2 and pi over 2. And then I simply extend it by periodicity. I literally copy and paste that curve into each of these lanes. There will be infinitely many branches. This here is pi. This here is pi plus pi over 4, so that's 5 pi over 4. That's 1. This here is 3 pi over 4. So this here is 2 pi. This here is 2 pi plus pi over 4. That's 9 pi over 4. This here is 2 pi minus pi over 4. That's 7 pi over 4. And the same on the negative side. So This is negative pi. This is negative pi plus pi over 4. This is negative pi minus pi over 4. So this is negative 3 pi over 4. This is negative 5 pi over 4. This point is negative 2 pi. This point is negative 2 pi plus pi over 4. That's negative 7 pi over 4. And that's negative 2 pi minus pi over 4. So negative 9 pi over 4. That is the graph of tangent x. Note, of course, that this only is a portion of that graph because there are infinitely many of these branches in either direction. Image of tangent is immediately clear to be the entire real line. Any of these branches will intersect with any horizontal line infinitely many times. So tangent x equals y always has a solution for x no matter what y is. There's that. And again, we see here in the picture the graph of tangent x. 3 branches of it. Let us now look at variations of tangent x. If instead of tangent x, we look at the function a tangent bx minus c plus d. Of course, this is nothing new. We just apply graph transformations to the graph that we already are familiar with. We know that the factor in front of a is responsible for a vertical stretch or compression, namely if absolute value of a is greater than 1. We stretch with a factor of a, and if absolute value of a is between 0 and 1, we compress. With a factor of 1 over absolute value a. And of course, if a is negative, we also reflect about the x-axis. We know all that. B, the factor in front of x inside the tangent function, corresponds to horizontal stretch or compression. So if b is positive, rather if b is greater than 1, we compress horizontally. So we speed up our function. If b by absolute value is between 0 and 1, we stretch with a factor of 1 over b. That is, we slow down. The period, of course, changes because of b. The period of the standard tangent function is pi, and it's divided by absolute value of b. As b is greater than 1, the period decreases, so we are getting faster. If b is between 0 and 1, then of course pi over absolute value of b is greater than pi. So we are slowing down. The period grows. Now the domain. Let's understand what is this. What is the domain of this function? The domain of this function bx minus c, or rather a tangent bx minus c plus d, is all the real numbers except where the argument of tangent equals pi over 2 plus an integer multiple of pi. So that is all the real numbers except those where x is different from pi over 2b plus c over b plus pn over b. And I can a little simplify this. X is different from c over b plus pi over 2b, 1 plus 2n. N is an integer, which I can write as c over b plus pi over 2b times L, where L is an odd integer. 1 plus 2n is always an integer which is odd, because 2n is always even, 2n plus 1 is always odd. The image is still the entire real line. Vertical asymptotes are numbers of this form, c over b plus pi over 2b times L. And that is about what we wanted to say about graphing variations of tangent. What's left to do is look at some numerical examples. In the first of these numerical examples, we need to graph one period of the function y equals -2 tangent of pi x plus pi minus 1. Let me add a page. Graph one period. We will perhaps graph more than one period, but one will be enough. The function y equals -2 tangent pi x plus pi minus 1. We note immediately that since tangent is pi periodic, tangent of pi x plus pi simply is tangent pi x. for any x in the, tangent pi x plus pi equals tangent pi x for any x in the domain of tangent pi x. So in fact, instead of graphing this, we may as well graph a simpler function. It'll be easier for us. We work with the function y equals -2 tangent pi x minus 1. Let's start with the domain. Domain is such that pi times x is different from pi over 2 plus integer multiple of half revolution, right? Because pi over 2 plus pi n is exactly where cosine is 0, and cosine is in the denominator in the definition of tangent. So when we divide this by pi, we get that x is different from 1/2 plus n. Any real number except those of the form 1/2 plus an integer. So domain of our function, let's call it f, is the entire real line minus the numbers plus minus 1/2, 3/2, and -3/2, and so on. Plus minus 5/2, plus minus 7/2, and so on. These numbers are vertical asymptotes. Just like for any tangent function, there will be infinitely many vertical asymptotes. And at this point, I very much want to start with the classical tangent function and perform a number of transformations. So I want to copy the classical tangent function here. And on the next step, I want to draw tangent of pi x. How will tangent of pi x be different from tangent x? Well, because of the factor pi in front of x, we must perform a horizontal compression by a factor of pi. So asymptotes will be, say, these two asymptotes, pi over 2 and negative pi over 2. they will turn into -1/2 and -1/2. And I need to choose a new scale. So that it's comfortable for me. Say, for instance, I will choose 1/2 to be 2 squares. So in particular, 4 squares is 1 unit. Up here I had 6 squares was pi. So 1 square was pi over 6. So in my situation, 1 squared will be 1 over 4. So instead of pi over 2 and negative pi over 2, I simply get 1/2 and -1/2. Other than that, the graph doesn't change. We simply compress it horizontally. At half the point, for instance, at 1/4, we'll have value 1, and at -1/4 we'll have value -1. And so on. Then the next asymptote will be 3/2 and -3/2. Value 1 will be here at 5 quarters, and value will be -1 at 3 quarters. And same here, a value will be here 1 and here -1. And this here is -3/4. This here is, sorry, this was -3/2. This is -3/4. This is -5/4. So this is tangent of pi x. So from now on, we will not be changing horizontal scale. So I can add a page and copy paste that picture onto the next page. Okay. Now we need to perform a vertical stretch by a factor of 2. From tangent of pi x, we get 2 tangent of pi x. Of course, this simply is vertical stretch by a factor of 2. Asymptotes are still where they were. Negative 1/2, 1/2. Negative 3/2 and 3/2. The only difference is that now, at these midpoints, 1/4 and 5/4, the value will be not 1 but 2. And likewise at these points, negative 5/4, negative 1/4, and 3/4, the values will be negative 2 instead of negative 1. So that is y equals 2 times tangent pi x. To get negative 2 tangent pi x, we simply reflect about the x-axis. That is the only transformation here. So let me copy this onto the new page. And now we reflect this about the x-axis. The asymptotes still where they were. So we have these key points. Now the points 3/4, negative 3/4, 1/4, and 5/4 are the points where the value is -2. 0, 3, so this is 0, 1, and -1 are of course the points where we have zeros. Now the points -5/4, -1/4, and 3/4 are the points where the value is +2. And so the graph will look like this. That is the graph of y equals -2 tangent pi x. And finally, the last transformation, which will make from -2 tangent pi x the graph of -2 tangent pi x minus 1, will be the transformation that will shift the last graph vertically by 1 unit downward. So let me add a page. And copy the last graph onto the next page. All right, so a new set of coordinate axes. Asymptotes stay where they were. Now, what happens with the graph? We shift it downward by 1 unit. So the all zeros, -1, 0, and 1, will be now the values, will be now the points with y coordinate -1. Also, the points -3/4, 1/4, and 5/4 will now have y coordinates -3. That's -3/4, 1/4, and 5/4. And the points -5/4, -1/4, and 3/4 will now have y coordinates 1. That is the graph of -2 tangent pi x, and we can add pi if you want, -1. It's worth investigating if zeros are good numbers here. Probably not. Zeros are not expressible in rational ways, so let's keep it this way. This left branch of this graph is what you see below the problem statement. Right, the points are -5/4, 1, -1, 1, and -3/4, -3. Exactly the ones that we have here. -5/4, 1, -1, -1, and -3/4, -3. All right, this example is now finished. In the next two examples, in this one and the one on the next page, we need to recognize the given graph as some variation of the tangent function. In the first of these two examples, we can look for a function in the form a times tangent of bx minus c plus d, because the graph indeed looks like some kind of tangent function, so it seems a reasonable choice. And we can start with finding the period. The period from the picture seems to be 8, because this is 0 and this is 8, and of course the difference is 8. On the other hand, we know that the period is pi over the coefficient b, which is responsible for horizontal compressions and stretches. So b by absolute value is pi over 8. And in fact, we may try immediately a function 1 times tangent, 1 here is a, pi over 8, which is b, times x, minus 0, which is c, plus 0, which is d. So in short, I'm trying a function tangent of pi over 8x. We can check by some evidence that this is indeed the right answer. Let's, for instance, check zeros. Tangent of pi over 8 times x is 0 if and only if the numerator of tangent, which is sine, is 0. And sine is 0, we know, if you recall the unit circle. Sine is 0 at 2 points on the unit circle, both of which could be collectively described as pi times an integer. If and only if pi over 8 times x equals pi times n, where n is an integer, which happens if and only if, canceling pi and multiplying by 8, x is 8 times n is an integer. So the zeros of this function are 0 plus minus 8 plus minus 16 plus minus 24 plus minus 32 plus minus 40 and so on. And indeed, we see this in the picture. Zeros are 0, 8, and negative 8. What about vertical asymptotes? Vertical asymptotes of this function, tangent of pi over 8x, are wherever pi over 8x equals the forbidden value of a tangent, pi over 2 plus pi n. Let's say pi k. K is an integer. Canceling by pi, multiplying by 8, we get x equals 4 plus 4k, where k is an integer. So in short, x equals 0. Now x equals 0 is, that's interesting. Let's check again. Pi over 8 times x equals pi over 2 plus pi k. That should be 8k, not 4k. When I multiply by 8, I should get 8k. So x is plus minus 4, and then multiples of 8, plus minus 12, plus minus 20, plus minus 28, and so on. And indeed, we see that the lines x equals 12, x equals 4, x equals negative 4, and x equals negative 12 are vertical asymptotes of this function. So this confirms that this graph is indeed that of tangent of pi over 8 times x. All right, what about the other example? It's also a variation of the tangent function. So we look for a function in the form a tangent bx minus c plus d, and the period here, which is pi over absolute value of b, is what? The difference between two consecutive zeros is pi over 2. So from here, absolute value of b is pi over 2, which is 2. And we should simply try tangent of 2x. So that is simply the standard tangent function compressed by a factor of 2. Asymptotes instead of pi over 2 and negative pi over 2 are now at pi over 4 and negative pi over 4. The period instead of pi is pi over 2. And that looks like our function, our graph. For either of the two examples, you can use Desmos to confirm that both guesses are correct. These are variations of the standard tangent function. We now turn our attention to the graphs of secant and cosecant. And recall that secant is 1 over cosine. So of course, when we think about the graph of secant, it won't hurt to remind ourselves the graph of cosine. Remember, cosine is an even function. And so secant will be an even function, naturally. Secant of negative x is simply 1 over cosine of negative x. And because cosine is even, that is simply 1 over cosine x, and that's secant x. For any x in the domain of secant. And by the way, what's the domain? Domain is all the real numbers except those where cosine is 0. And cosine is 0 at points pi over 2 plus an integer multiple of half a revolution. So the zeros of cosine, pi over 2, negative pi over 2, 3 pi over 2, negative 3 pi over 2, become vertical asymptotes of secant. That is because if you think of what happens when x approaches any of these points, pi over 2 plus pi n, practically the same thing as with tangent. Tangent is sine over cosine, and secant is 1 over cosine. You are dividing 1 over numbers that are closer and closer to 0. Of course, you will get positive or negative infinity, depending on whether cosine is positive or negative. So the vertical lines x equals pi over 2 plus pi n, where n is an integer, are vertical asymptotes. And also, I find it helpful to know that, for instance, if cosine is positive, then secant, which is 1 over cosine, will be greater or equal than 1. And if cosine is negative, then secant will be less than or equal to -1. They touch each other at points where cosine is 1 or -1. Of course, say in the first quadrant, as cosine decreases from 1 to 0, secant increases from 1 to infinity. Now, by the fact that secant is even, reflecting this piece about the y-axis gives us this piece. And we can also draw secant when cosine is negative. This is quadrant 2. Cosine is decreasing from 0 to -1. Correspondingly, secant, the reciprocal of cosine, increases from -infinity to -1. And here, in the third quadrant, cosine increases from -1 to 0, staying negative. So its reciprocal is also staying negative, but decreases from -1 to -infinity. Once we have secant drawn from -π/2 to 3π/2, we can extend it by periodicity. We know secant is 2π periodic. So you can copy paste this portion of the graph in either direction, and it'll give you the entire graph of secant x. The analysis for cosecant is very similar. We just recall that cosecant is 1 over sine x. And recall that zeros of sine x are precisely the points of the form pi times an integer. So of course, these are points that are missing in the domain of cosecant. And moreover, these are vertical asymptotes. X equals pi k when k is an integer. Other than that, the analysis is the same. When sine is positive and less or equal than 1, cosecant is greater or equal than 1, and when sine is negative but greater or equal than -1, cosecant is less or equal than -1. Cosecant is odd, just like sine is odd. So it's enough to figure out the graph of cosecant on the interval from 0 to pi, both of which are, by the way, vertical asymptotes. Of course, at point pi/2, cosecant is 1 because sine is 1. In the first quadrant, as sine increases from positive 0 to 1, the reciprocal is decreases from positive infinity to 1. And in the second quadrant, as sine is decreasing from 1 to positive 0, the reciprocal is increasing from 1 to positive infinity. Once we have the graph of secant from 0 to pi, we can reflect about the origin, get this piece, and this is enough because secant is of course 2 pi periodic. Once we get it from negative pi to pi, we can copy paste that piece and extend in either direction and get the entire graph of cosecant x. Note again that you don't need to memorize what the graphs of secant and cosecant look like. You can always reconstruct them from those of cosine and sine respectively. And of course, what the graphs of cosine and sine look like, you do need to memorize. Now, whenever you need to graph a variation of secant or cosecant, we know what to do. These are just transformations of the standard graph. The stretching factor is the absolute value of the factor in front of the function. Horizontal stretch is governed by b. The period compresses or stretches according to whether b is greater than 1 or less than 1. According to b, we change the domain, just like for the tangent function. That is the same idea here. And again, in general, I wouldn't recommend memorizing this. You perform modifications of the standard graph as you go. We will see this in examples. And there are two of them. In the first of them, we need to graph one period of the function 4 times secant of pi over 3x minus pi over 2 plus 1. And before we jump into drawing graphs, I would like to offer a small algebraic transformation which will simplify our work. We will not need to perform a horizontal shift because of this pi over 2, because we can do the following. We can write secant as 1 over cosine pi over 3x minus pi over 2 plus 1. That is the definition of cosecant. Now, because cosine is even, I can flip the minus sign, the negative sign in the argument of cosine, and say that cosine of alpha minus beta is cosine of negative beta minus alpha. Factor out the minus. But now by the fact that cosine is even, I can ignore the minus and write that this is cosine of beta minus alpha. If I do this here, I simply flip pi over 3x and pi over 2 and get cosine of pi over 2 minus pi over 3x. Now, Cosine of pi over 2 minus some angle by a co-function identity is simply sine of that angle we subtract from pi over 2. So that is sine of pi over 3x plus 1. And I get simply 4 times cosecant of pi over 3x plus 1. So instead of graphing the original function, we will be graphing this. Of course, the graphs are the same, but this, in my opinion, is a little bit easier. So let me add a page. We will be sketching the graph of four cosecant of pi over 3x plus 1. The plan is the usual. We first graph cosecant x, then we graph cosecant of pi over 3x, then we graph 4 cosecant of pi over 3x, and then finally the desired graph, 4 cosecant of pi over 3x plus 1. And let's discuss what transformations we will need to make. How do we get from cosecant to cosecant of pi over 3x? We perform a horizontal compression or stretch. Because pi over 3 is more than 1, there will be a compression with a factor of pi over 3. And so the new period will be the old period 2 pi divided by a factor in front of x, which is pi over 3. And so the new period will be 6, which is slightly less than 2 pi. As expected, we're compressing, so the function is speeding up. Cosecant of pi over 3x will be a little bit faster than cosecant x. That is the only non-trivial transformation. The other two are very simple. This is simply vertical stretch with a factor of 4, and this here is a vertical shift by 1 unit upward. The last two transformations don't change the scale, so that is good. And let's draw the graph of cosecant. We should immediately think about horizontal scale. I usually choose pi over 2 to be 3 squares, so pi is 6 squares. Let's keep it that way. So vertical asymptotes will be at 0, at pi and negative pi, at 2 pi and negative 2 pi, and so on. All right, at value pi over 2, our function will be at 1. So sine would go like this. Accordingly, 1 over sine would go like this. It's not really a parabola, of course, but it resembles a parabola. And now we reflect about the origin and get a shape like this. Now, we simply extend by periodicity. So this here is 3 pi over 2. So we will have this. And this here is negative 3 pi over 2, and we will have this. So the scale here is 6 squares equals pi. So 1 square equals pi over 6. That is the graph of cosecant x. Now, when we horizontally compress it, the period will be 6 instead of 2 pi. And for instance, the vertical asymptote pi will in fact be vertical asymptote x equals 3. Because when x is 3, we get cosecant pi, and that's 1 over sine pi, and that's undefined. So what I offer is just copy-paste this same graph and only change labels. Do not change the picture itself. So what happens now, I say that 6 squares will be not pi, but rather 6. So that 1 square is 1 unit. So accordingly, instead of pi and 2 pi and negative pi and negative 2 pi, I will have 3, 6, negative 3, and negative 6. And accordingly, instead of negative 3 pi over 2, negative pi over 2, pi over 2, and 3 pi over 2, we get the following labels. And that is the graph of cosecant of pi over 3x rather than x. Now the other two transformations will not change the horizontal scale, so we'll keep it. Now I can take this picture and copy paste it onto the next page. So this will be the graph of 4 times cosecant of pi over 3x. I need to redraw the curves. So instead of value 1, this curve will start at value 4. Maybe I should change vertical scale. I should say that this is 2, so that this is 4, and my curve will start here. All right, so this is 4 cosecant, not cosine, of course. And finally, to get 4 cosecant pi over 3x plus 1, we need to shift this last graph by 1 unit upward. And I should carefully redraw all curves again. So, for instance, the upward curves will start at 5. and the downward curves will start at -3 rather than -4. So this piece of the graph that's in green now is what you see below the problem statement. That is what we have here. Period is 6, asymptotes are 0, 3, and 6. This is 5, and this is -3. This example is now over. In the second example, we need to draw the graph of 2 cosecant pi over 2x plus 1. Let's briefly discuss how we do that. Of course, we will start with the graph of cosecant x. And then to get the graph of cosecant of pi over 2x, we need to apply a horizontal compression with a factor of pi over 2. That will, of course, change the period. The next transformation will be a vertical stretch by a factor of 2. And after that, a vertical shift by 1 unit. Here is the graph of cosecant. You can easily recognize it. If you look at the graph of sine, now the scale here is, as always, 1 squared is pi over 6, so that 6 squares on this paper corresponds to pi. When we compress this by a factor of pi over 2, we change the period. So the period here is, of course, 2 pi. When we apply the transformation, the period will be the whole period 2 pi divided by the factor in front of x, pi over 2. So the period will be 4, which is, of course, less than 2 pi. So our function will be faster. And you can easily see that I did not change the scale, I simply changed the labels. Now, in this picture, 6 squares corresponds to 2 rather than pi. So 1 square corresponds to 1/3 of a unit. And you can think about what will that be. That, I believe, will be sine x sped up by a factor of 2, or by a factor of, pi over 2. So perhaps this is sine of pi over 2x. Zeros are all multiples of 2. Right? Now, the next transformation is vertical stretch by a factor of 2. So we'll take that picture and stretch by 2 so that these will start at 2 rather than 1, and these will start at -2 rather than at -1. Here is the picture. Correspondingly, we will get our sine function as what? That is the question. 2 sine of pi over 2x. Zeros are still multiples of 2, and we stretch it by a factor of 2. Now what we need to do with this function is simply raise it by 1 unit up, so that these will start at 3 rather than 2, and these will start at -1 rather than at -2. And the corresponding sine function will have its midline at 1, let's use a different color. So you can easily see that this function is 2 sine pi over 2x plus 1. And that is, in green, our desired function, 2 cosecant pi over 2x plus 1. So this function here in blue actually is 2 sine of pi over 2x plus 1. And this example is now over. We now turn our attention to the study of the graph of cotangent x. Remember, cotangent is cosine over sine, or alternatively, you can define cotangent as the reciprocal of tangent. And either definition will tell us a lot about the properties of cotangent. We know it's pi periodic because tangent is pi periodic. We know it's odd because tangent is odd. And the domain of cotangent is all the real numbers except those where the denominator sine is 0. And remember, sine is 0 if and only if its argument is an integer multiple of pi. So such numbers, such real numbers, and only them, and only they, are where cotangent is not defined. So cotangent is defined for any real number except those that are integer multiples of pi. Also, it won't hurt to recall the geometric definition of cotangent. If we have the unit circle centered at the origin, cotangent is the following distance. If this here is x, then this distance is cotangent x. We can easily see that because, again, equality of triangles, or the similarity of triangles, OAB and triangle OCD are similar, and in triangle OCD, this angle here is x. So we know that by similarity of triangles, say CD by CO, CD by CO equals AB by AO. This triangle is similar to the big triangle. But of course, AO is 1. So that's just simply AB. Now CD is the x-coordinate of that point. We know that's cosine x. And CO is the y-coordinate of that point. And we know that's sine x. So AB is therefore the ratio of cosine and sine, simply cotangent x. So that definition might be helpful when we try to understand how the graph of cotangent looks like. Vertical lines x equals pi k, where k is an integer, will be vertical asymptotes. That's where cotangent is not defined. And that's where the limit of cotangent is infinity. We can easily see that when x approaches an integer multiple of pi, the limit of cotangent, being the limit of cosine over sine, is infinity. Why? Because at any such point, cosine is either -1 or +1. Sine at any such point is close to 0, positive or negative. Just like in the case of tangent, when you divide a number that is close to positive or -1 by a number that is close to 0, you get infinity. So pi k will be vertical asymptotes. And because cotangent is pi periodic, it will be enough to draw the graph of cotangent on the interval 0 pi, excluding, of course, the endpoints, because the endpoints are where cotangent is undefined. And then extend by periodicity. So what happens with cotangent in the first quadrant? Let's think. Let's say we start here with very, very small positive x's in the first quadrant. For very, very small positive x's, cosine is close to 1, sine is positive and close to 0. The ratio is huge and positive. Cotangent here is positive infinity. As we increase in the first quadrant, cosine stays positive but decreases to 0. And sine stays positive but increases to 1. The value at pi over 2 in particular is simply 0. Cosine of pi over 2 is 0, sine is 1. So we have 0 at pi over 2. Now what happens in the second quadrant? In the second quadrant, cosine is now negative, and it gets more and more negative from 0 to negative 1. Whereas sine is positive but gets closer and closer to 0. So we're dividing numbers that are close to negative 1 by a number that's slightly above 0. Of course, the result will be a huge negative number. So to the right of pi, to the left of pi, a little short of pi, the behavior of cotangent will be negatively infinite. That's what we see in the picture. And accordingly, we extend cotangent by periodicity using the fact that cotangent is pi periodic. There's one thing that I want to note is that in principle the shape of cotangent is the same as that of tangent. More precisely, if I draw a curve like this, which is clearly negative cotangent, and shift it to the left by a quantity of pi over 2, that will be exactly tangent. In other words, negative cotangent of x and the shift to the left by pi over 2 corresponds to adding pi over 2 is exactly tangent x. If we here change x plus pi over 2 by y, so that x is y minus pi over 2, we get negative cotangent y equals tangent of y minus pi over 2, or in other words, cotangent y is negative tangent y minus pi over 2, which again shows that in principle the graph of cotangent is a modification of the graph of tangent. And in general, we will look at some modifications, or you will look at them in your homework, modifications of cotangent, where of course again the factor in front of cotangent is responsible for vertical stretch, B changes the period, C is horizontal shift, D is a vertical shift. Let's look at an example here of a specific cotangent function. Sketch a graph of one period of the function 4 times pi over 8x minus pi over 2 minus 2. We will sketch more than one period. So let me add a page. Four times cotangent pi over 8x minus pi over 2 minus 2. In fact, we will explain that we don't need this phase shift. We can actually do some algebra here. And note that cotangent of pi over 8x minus pi over 2 actually is cotangent of negative pi over 2 minus pi over 8x. All I did was factor out -1 from the expression inside cotangent. And now I'm going to use the fact that cotangent is odd. And so the minus inside cotangent can be taken out. So that'll be negative cotangent pi over 2 minus pi over 8x. The whole point of this transformation is to now use the co-function identity. Because as we know, cotangent of pi over 2 minus x is tangent x, and likewise tangent of pi over 2 minus x is cotangent x, whenever these expressions make sense. So we get here negative tangent pi over 8x, and that quite significantly simplifies our life, because we will work with our function f in the form 4 times negative tangent pi over 8x minus 2, which of course is the same as -4 tangent pi over 8x minus 2. That is the graph we work with. That is the function we work with. And our plan, as usual, will be a sequence of transformations. We'll start with the graph tangent x. Then we will perform a horizontal compression by a factor, a horizontal stretch perhaps, by a certain factor. We'll see which one. That'll give us the graph of tangent pi over x. pi over 8 times x. Then we will perform a vertical stretch to get 4 times tangent of pi over 8x. Then, of course, to get negative that, we will perform a reflection about the horizontal axis to get negative 4 tangent of pi over 8x. And finally, we will perform a vertical shift by 2 units downward to get negative 4 tangent pi over 8 x minus 2. All right, let's start with the graph of tangent x. And again, I should carefully think about my horizontal scale. If I, as always, choose 6 squares to be pi, so that 1 squared is pi over 6, what scale will I use when I draw the graph of this guy? How does the graph of this guy differ from this guy? Well, the period changes, right? The period of this guy will be pi over 8. So instead of period pi, we will get period 8, which is a lot greater. So our function slows down quite a bit, which is not surprising because pi over 8 is a lot less than 1. So let's think. Asymptotes of this graph, tangent x, are, for instance, at negative pi over 2 and pi over 2. And that's usually in our scale 3 squares. What about tangent of pi over 8x? Where will that have asymptotes? It will have an asymptote whenever the argument, say, is pi over 2, which happens, for instance, when x is 4 or negative 4. Correct? Because when x is 4, we get here pi over 2, and tangent of pi over 2 is undefined. Same with negative 4. And maybe that I will have 4 squares. So my scale for this graph will be very simple. 1 square is 1 unit. I think that'll work. So let's start drawing. So asymptotes at pi over 2 and negative pi over 2. Then at 3 pi over 2 and negative 3 pi over 2. Then 5 pi over 2 and negative 5 pi over 2. And I again forget about the magic point pi over 4, 1, and negative pi over 4, negative 1. It's nice to have them. So these are points (3 pi over 4, negative 1) and 5 pi over 4, 1. These are points pi plus 2 pi plus minus pi over 4, so 9 pi over 4 and 7 pi over 4. And the same on the negative side. So here is negative pi, negative 3 pi over 4, and negative 5 pi over 4. And here, this is negative 9 pi over 4 and negative 7 pi over 4. All right, this is tangent x. Now, in this picture, 1 squared equals pi over 6, so 6 squared equals pi. In my next picture, the scale that makes sense to choose is 1 square is 1 unit. So the asymptotes will be at 4 and negative 4. And then at 8, no, not at 8. Tangent pi is actually defined at 12 and negative 12, because this function will be with what period? Pi over 8, so period is 8. This is now 12 and negative 12. And where are these points where tangent is 1 and -1? These are simply points 2 and -2, for instance. Very convenient. This point is 6 and this point is 10. And this point is -8, this is -6, and this is -10. This time the scale is 1 square is 1 unit. This is the graph of tangent of pi over 8 times x. From now on, we won't need to change the horizontal scale. When we do the other transformations. And so the next transformation we need to do is what? Raise vertical stretch by a factor of 4. So that doesn't change the asymptotes. But it will change the curves. So now, where tangent used to be 1, it will be taken value 4. And maybe now I should change the vertical scale. Also 1 unit 1 squared. That is y equals 4 tangent pi over 8x. vertical stretch by a factor of 4. And to put the minus in front of it, I simply reflect about the x-axis. So now we will have values 4 at points -10, -2, and 6, and values -1 at points -6, 2, oh, that's a mistake. Value 4 should be here. That is the graph of -4 tangent pi over 8x. And the final step is to simply shift it downward by 1 unit. So let me add another page and copy paste this onto the new page. So what are the points of interest here? The 0 will be at -1. That's a point of interest. Now, -5 is a point of interest. And also 3 is a point of interest. Value at say 2 will be -5. That is, let's just check this. So we want this to be the graph of what was it? -4 tangent. We actually okay, -4 tangent pi over 8x -2. So we should be raising downward by 2 units, not by 1. -6 and this is 2. So points of interest are -2 and 2, 0, -2, and 2, -6. Let's see if that's actually true. Y of 0 is -2 indeed. Y at -2 is -4 times tangent of pi over 8 times -2 minus 2. That's -4 times tangent of -pi over 4 minus 2. That's -4 times -1 minus 2. That is 4 minus 2, that's 2. Looks good. And y at 2 is -4 times tangent of pi over 8 times 2 minus 2. That's -4 tangent of pi over 4 minus 2. That's -4 times 1 minus 2. That's -6. Looks correct. The scale that I chose makes it difficult to produce a nice curve. Nonetheless, it shouldn't be a problem for us. And that is the graph of -4 tangent of pi over 8x minus 2, which is the same as 4 cotangent of pi over 8x minus pi over 2 minus 2. And this right branch is what you see drawn in blue below the problem statement. Note, of course, that the scale in this picture is different. For instance, this point here is 8, -2. This point here is, let's see, 6, 4. No, 6, 6, 2. And this point here is 10, what was it for us? 10, -6. The scale along the y-axis, as you see, is very small, so it's difficult to understand that this is 2 and this is -6. And this is -2. All right, hopefully you will practice more of these in your homework, and this example is now over, and we're done with our study of the graphs of secant, cosecant, tangent, and cotangent. Thank you.